start with samples. And we go fluorescence images, so I'll show you what.
Bacteria are capable of sensory behaviour, so they can make decisions about whether they want to go and live somewhere or not. And so this is really all about bacteria making choices about which kind of surface they think is good to live on or not good to live on.
Okay.
We basically incubate the bacteria with a slide with thousands of different polymer spots on them and look to see which ones they don't like. So some they love, some they like a little bit, and some they clearly seem to avoid.
And this is what you're seeing. So the bacteria actually are moving outward, so they've been inoculated in the corner, and the shape change as well. They elongate during the swarming, so they differentiate.
They stick to the surface, they grow a little bit, and they become reversibly attached. Think about whether they like it there or not, and then over time start to think, yep, this is a good place, I'll squirt out some glue, and we'll become stuck just like araldite to the surface, and then we'll bloom just like a sort of a flowery growth all over the surface. And then what they start to do is, just like tumours do, they start to differentiate into a thick, slimy structure, which is almost impossible to eradicate.
They're all aligned in rafts of cells together, but here they're just completely disorganized and not aligned, so they're not creating this swarm pattern, which you can see, and they're actually coming loose, but it's just not swimming.
We found a polymer that was particularly well suited to the environment where a urinary catheter would find itself when implanted in a human, and that polymer is optimal for that environment. We've looked at other environments, such as that for a breathing tube or an endotracheal tube, where we believe a slightly different formulation of the polymer would be optimal, would perform the best.
Under a microscope. You can show the swarming front.
Yes,
Third one. But then show the anti-bacterial. Mention microbiology.
So if you think of that thick, slimy structure stuck on a catheter in a body, your immune system can't get rid of it, and antibiotics don't kill it. And so that's what you want to stop.
Increase in hospital stay, an increased risk of death, and then long-term disability related to these infections. From a healthcare perspective, there's an increase in length of stay from around 8 to 15 days, and that incurs an increase in costs associated with these. So for the NHS, annually, it's around £1 billion worth of extra money. By using interventions that don't rely on antibiotics to to prevent these types of infections will have a huge impact on antibiotic stewardship and antimicrobial resistance in the longer term. So these types of interventions where we're essentially preventing an infection from developing are actually key to controlling antibiotic resistance in the longer term.
There are probably about 6 to 8 species of bacteria that are commonly found in association with catheters, and a few different organisms. For example, Candida is another organism which is a fungus that also pops up in these. So it's a very limited group of organisms. So we chose the ones that are the main problem.